Hello everyone and welcome back to the A+ Tutor. In today's video, we're going over indefinite integrals. Previously, I've gone over how to find the derivative of a function, but what if we want to do the opposite? We can do that. We can find what's called the antiderivative or the integral of a function. In general, if we know that f of x is equal to x squared, then f prime of x, or the derivative of x, is equal to 2x by the power rule. So, what if we go backwards? What if we know that f prime of x is equal to 2x? Then how can we figure out that the original function f of x is equal to x squared? In this case, we know because we took the function f of x, so we already know what our original function is. But what if we had a function f of x equals x squared plus 4? Well, here f prime x is also equal to 2x. Our derivative is also 2x. But these two functions, f of x equals x squared and f of x equals x squared plus 4, are not the same function. We have that plus 4 at the bottom. So how do we find these integrals or find these antiderivatives where we know exactly what our function may have been? In this case, this lets us know that we have to, when finding antiderivatives or finding our original function, we have to consider that a constant term may be present at the end of our function, and that's for any function that we find the derivative of. So let's take an example. Let's say we need to find the antiderivative of f of x equals x to the fourth plus 3x minus 9. Typically, when we're finding antiderivatives, we'll see our problems written in this form. The integral, that kind of big F, is our integral sign of f of x dx. So we're finding the integral of f of x with respect to x. And in this case, our integral is 1/5 x to the fifth plus 3/2 x squared minus 9x plus c. So how do we get to this point? How do we figure out that our integral, or their antiderivative, is this function right here? So first, let's take each term by itself. If we know that f prime of x is equal to x to the fourth, because in this case, we're taking the antiderivative, right? So that means this is like our f prime of x. This is our derivative of our original function. We know that f prime of x is equal to x to the fourth. So what can we take the derivative of to give us x to the fourth? Well, when we use the power rule, we know that f of x, let's say x to the fifth, when we derive that, f prime of x would equal 5x to the fourth. We want x to the fourth, not 5x to the fourth. So the only way that we get 5x to the fourth is if we have a 1/5 out in front. So now, instead of having 5x to the fourth, we would have 5 times 1/5 x to the fourth, which would equal x to the fourth, and that's exactly what we're looking for. So when we're taking our antiderivative, we have to consider how do we get the exact function we're looking for, which is x to the fourth. The derivative of what is going to give us just x to the fourth by itself, and we saw here that's going to be 1/5 x to the fifth. So we can do the same thing with each of these terms. If f prime of x is equal to 3x, then what must f of x be equal to? Again, we cannot say just 3x squared, because if we were to derive that, we would get 6x, and we want 3x, not 6x. So if we take that 1/2 out in front, because we've got a 2 here, then when we take the derivative of 3/2x squared, we would get 3x. And the same thing with our last term. If f prime of x equals -9, then what must f of x be equal to? Whenever we take the derivative of a function and we end up with a constant number, that function is a linear function. Our function must be x, but the derivative of just x would equal 1. So that has to be -9x because we need to just be left with that -9. And then lastly, the derivative of any constant term is 0. So that's why we always have to have this plus c at the end, because we need to account for any extra constant terms that we may have in our function. And if we work backwards, we take this now, capital F of x, we would find that capital F prime of x would be equal to the derivative of our first term, which is going to be 5 times 1 over 5 x to the 4th power, using the power rule, plus the derivative of our second term, which is 2 times 3 over 2 x, again using the power rule, minus 9, using the power rule, which is equal to x to the 4th plus 3x minus 9, which is exactly what we started with. So when we work backwards, we want to think about doing the opposite of our derivative. So we know that our derivatives tell us the slope or the rate of change of a function, so how fast or slow some function is moving, and that way we can understand the rate of change at certain points. Our integral will tell us the area underneath a certain function. And this is really helpful because this will tell us the accumulation of a function between a set of points or up until a certain point. So we may want to know the rate of change of a function to understand functions over time, but we also want to know how functions will grow or accumulate over time as well, and that's what our integrals can tell us. There are going to be some rules that we can use, just like with our derivatives, there are some rules that we can use to find our antiderivative because we want to work backwards. And I'll show you what those rules are now. So for derivatives, we had rules like the chain rule, the power rule, the product rule. We have some similar rules here that will make it really easy for us to solve our integrals. So let's start with our constant rule. For our constant rule, if we have the integral of some k with respect to x, then our integral will always be that constant k times x plus c. If we take the integral of 3 dx, then this will be equal to 3x plus c. Next, we have the constant multiplication rule. Our constant multiplication rule states that if we have the integral of some k times f of x dx, then the value of our integral, we can move that constant to the outside and write this as k times the integral of f of x. So as we're solving integrals and as we start to use these rules, we'll be able to take any constants and kind of bring those to the outside to hold those so that we don't have to worry about those as we're solving our integral. So for example, if we're taking the integral of 4x squared dx, x squared is our function and 4 is our constant, so we can write this as 4 times the integral of x squared dx. Next, we have our sum and difference rule. Our sum and difference rule states that if we have the integral of f of x plus or minus g of x dx, then we can break this apart and write this as the integral of f of x plus or minus the integral of g of x. So if we have something like the integral of 4x squared plus 3x dx, then we can write this as the integral of 4x squared dx plus the integral of 3x dx, and solve each of these by themselves. Next, we have the power rule. This rule is going to be the most used rule with our integrals. This is really what's going to drive solving our integrals. We use a combination of our first 3 rules, constant, multiplication, and then sum and difference, but then this power rule is really going to help us to solve these derivatives. So For our power rule states if we have the integral of x to some n power, then that is going to be equal to x to the n plus 1 power over n plus 1 plus c, and n cannot be equal to -1. So this is what we really used in our example earlier to solve that derivative. Instead of having to think backwards and think about what functions would make that derivative, we can use the power rule. If we're taking the derivative of x to the third power, then this is going to be equal to x to the 3 plus 1 over 3 plus 1 plus c, or x to the fourth over 4 plus c. Anytime we're solving an integral that has some power, we can use the power rule to solve in combination with some of our other rules. Next, we have the log rule. So this is why we cannot consider n equals -1, because if n equals -1, we'll have x to the -1 power or 1 over x. This is a separate rule, which is our log rule. So our log rule says the integral of 1 over x dx is equal to the natural log of the absolute value of x plus c, and x cannot equal 0. Say we have the integral of 7 over x dx. Then we can consider our constant multiplication rule. This would be 7 times 1 over the integral of 1 over x dx, which is equal to 7 ln absolute value of x plus c, and x cannot equal 0. Next, we have our exponent rule, and we have two cases that we have to consider here. So first we have the integral of a to the kx dx, where a is some number raised to some power. You could say 2 to the x, 3 to the x to the 3x power, things like that. A is just some power. So our integral is going to be equal to a to the kx over k ln a plus c. And here x cannot be equal to 0. We also have to consider the integral of e to the x power dx. And if we remember, the derivative of e to the x is e to the x, and the same is true for our integral. Our integral of e to the x is just going to be e to the x plus c. Whenever we're solving integrals, we can never forget that constant term, that plus c, because that's going to always cover whatever our function may have been. So we always have to include plus c for our indefinite integrals. So then we also have some trig rules that we use to solve any trig integrals that we have. So let's go over all of our trig rules. So the integral of sine x dx is going to be equal to negative cosine x plus c. The integral of cosine x dx is equal to sine x plus c. The integral of secant squared x dx is going to be equal to tan x plus c. Next, we have the integral of secant x tan x dx, and that is equal to secant x plus c. We have the integral of cosecant squared x dx, and that's equal to negative cotangent x plus c. The integral of cosecant x cotangent x dx is equal to cosecant x plus c. And then remember, we had our inverse trig functions, our arctan, arcsine, all of those. So the integral of 1 over 1 plus x squared dx is equal to arctan x plus c, or the inverse tan plus c. And the integral of 1 over the square root of 1 minus x squared dx is equal to arcsine x plus c. So these are some of the trig functions that we'll consider for our integrals. There are going to be some more advanced rules and some other scenarios that may need to be handled, but we'll go more in depth in those in a later video. This is just going to give us an introduction to our indefinite integrals and show us how to start solving our integrals. Let's take some examples of some integrals. First, we have the integral of x to the fourth minus x to the third plus x squared dx. So this is going to use our sum and difference rule and our power rule. So we can write this as the integral f of x dx plus or minus the integral of g of x dx plus or minus the integral of h of x dx. So we would have the integral of x to the fourth dx minus the integral of x to the third dx plus the integral of x squared dx. Now we can use the power rule. We can say for each of these, the integral of x to the n dx is equal to x to the n plus 1 over n plus 1 plus c. For our first term, n is equal to 4. For our second term, n is equal to 3. And for our third term, n is equal to 2. So this will become x to the fifth over 5. 4 plus 1 is 5 over 5. Minus x to the fourth over 4. Plus x to the third over 3, all of this plus c. Even though we have multiple terms, we only need to write our plus c once because we're always just adding one constant. And this would be our final answer. Next we have the integral of 7x to the 3/2 power plus 2x to the 1/2 power dx. So again, we're using a few rules here. First, we have our sum and difference rule. So we'll be able to rewrite this as the integral of f of x dx plus the integral of g of x dx. So this becomes the integral of 7x to the 3/2 power dx plus the integral of 2x to the 1/2 power dx. So next, let's look at two different rules. We'll consider our constant multiplication rule, which we can use to rewrite our constants on the outside. So this will be k times the integral of f of x dx. And we'll use our power rule again, which says the integral of x to the n dx is equal to x to the n plus 1 over n plus 1 plus c. So we'll use both of these rules here. This 7 is our k, and our n is equal to 3 over 2 for our first term. This 2 is our k in our second term, and our n is equal to 1/2. So we're able to start to solve this. We'll take our 7 and pull that to the outside, times x to the 3 over 2 plus 1 over 3 over 2 plus 1 power, plus 2 on the outside times x to the 1/2 plus 1 over 1/2 plus 1 power, all of that plus c. So we can simplify our fractions. That'll give us 7x to the 5/2 power over 5 over 2 plus 2 times x to the 3/2 power over 3 over 2, which is going to be equal to, if we now simplify, get those fractions out of our denominator, essentially do a keep, change, flip, we'll get 14x to the 5/2 power over 5 plus 4x to the 3/2 power over 3. And that's our final answer. So even though we have to work with some fractions, all we have to do is simplify and solve them, take it one piece at a time, and we get to that final answer. Next, we have the integral of 3 over x dx. So again, we're going to be using two different rules here. We'll use our constant multiplication rule, which says we can pull that constant out and we'll get k times the integral of f of x dx. So that's going to make this function 3 times the integral of 1 over x dx. And then we'll also use our log rule. Our log rule says the integral of 1 over x dx is equal to the natural log of the absolute value of x plus c. So our function will become 3 times the natural log of x plus c, or we can just write that as 3 ln absolute value of x plus c. Next we have the integral of 2 sine x plus 3 cos x dx. So again, we're going to use a combination of rules. We'll use our sum and difference rule, our constant multiplication rule, and our sine and cosine derivatives. So let's start to break this apart. We'll use our constant multiplication rule by bringing that k to the outside. And our sum and difference rule to write this as f of x dx plus the integral of g of x dx. So this will become 2 times the integral of sine x dx plus 3 times the integral of cos x dx. And then our integral for sine is negative cosine x plus c, and our integral for cosine is equal to sine x plus c. So this will become 2 times negative cos x plus 3 times sine x plus c, or negative 2 cos x plus 3 sine x plus c. Next we have the integral of 5e to the x minus 2. So we'll use our sum and difference rule to break these up, our constant multiplication rule to bring that k out to the front, and our constant rule to find the derivative of a constant. So we can rewrite this as 5 times the integral of e to the x dx minus the integral of 2 dx, and then this will solve. We know that the integral of e to the x dx is equal to e to the x plus c. So we can solve this and write 5e to the x minus 2x plus c as our answer. Now we have the integral of 7 over the square root of 1 minus x squared dx. So again, we have our constant multiplication rule. So this helps us because we can rewrite this as 7 times the integral of 1 over the square root of 1 minus x squared dx. And that means that we can identify what integral this actually is. And this is one of our trig integrals. This is our arc sine or our inverse sine. So the integral of 1 over the square root of 1 minus x squared dx is equal to our inverse sine, sine to the negative 1x plus c. So let's solve this derivative. This is going to be equal to 7 times sine to the negative 1x plus c, or 7 arc sine c. Either way is correct, and that's our answer. Next we have the integral of the cube root of 7x dx. This may not be as obvious at first in terms of how we can break this up. So the first thing we want to do is we want to try and get our x by itself. We want to get just an x term, even if it has an exponent. So what we can do is we can rewrite this as the integral of the cube root of 7 times the cube root of x dx. And so now we can see that our cube root of 7 becomes our k, or our constant term, and our cube root of x is our f of x term. So we can use our constant multiplication rule to break that up, which means we would rewrite this as k times the integral of f of x dx. So this would become the cube root of 7 times the integral of the cube root of x dx. But we can rewrite the cube root of x as x to the 1/3 power. So now we can write this as a power, and this lets us use our power rule, because we know that for our power rule, the integral of some x to the n dx is going to be equal to x to the n plus 1 over n plus 1 plus c. So now that we know what our power is, we are able to solve this integral using the power rule. So we'll keep our cube root of 7 on the outside times x to the 1/3 plus 1 over 1/3 plus 1 plus c, which is equal to the cube root of 7 times x to the 4/3 power over 4/3. Or when we bring that fraction out of the bottom, we would say 3 times the cube root of 7 times x to the 4/3 over 4. And that's our answer. You might notice for the power rule, every time we've taken the power rule, we end up having to flip whatever fractions in the denominator. So we can consider that the reciprocal. So if we're going to have x to the 4/3, it's going to be 3/4 x to the 4/3, or x to the x squared becomes 1/2 x squared. So we always have the reciprocal of our power. So that's one way that you can consider it to make it really easy to find your power rule integrals. And here's our last example. We have the integral of 7 cosine x plus 4 e to the x dx. So again, we're using that constant multiplication rule. We'll use our cosine integral, and we'll use our sum and difference rule, and we'll use our exponent rule as well. So we'll have k times the integral of f of x dx, the integral of f of x dx plus the integral of g of x dx. We'll have the integral of e to the x dx equals e to the x plus c, and the integral of cos x is equal to sine x plus c. So these are all the rules that we'll be using here. So let's start with our constant multiplication rule and our sum and difference rule. This will give us 7 times the integral of cos x dx plus 4 times the integral of e to the x dx, which is going to be equal to 7 times the integral of cosine x is sine x, plus 4 times the integral of e to the x is e to the x, plus c. So our final answer will be 7 sine x plus 4 e to the x plus c. Thank you so much for watching. I hope you enjoyed and I hope you learned something. If you have any questions, leave them in the comments below. Don't forget to like this video if you liked it, and make sure you're subscribed to my channel so you never miss a video. See you next time.